My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 416. In this lecture, we will try to understand random forest and its cases. If you think about random forest, it is basically nothing but decision tree with row sampling, column sampling, and aggregation. All these three means row sampling, column sampling, and aggregation were mainly done to reduce variance of your base models. So whenever the properties or cases that we have seen for decision trees, for example, decision trees do not handle large dimensionality very well. We have seen this especially when you have categorical features with many categories. Doing one hot encoding is not good idea for decision trees. Decision tree is the base model for random forest. So all the cases that we have seen for decision tree holds for random forest except for couple of them. We will go into couple of them. In general, wherever decision tree fails to work well, random forest also fails to work well. But of course, as you obviously understand, the bias variance trade off of random forest is not same as decision tree, because this depends on k. What is our k? Number of base learners. We have already seen a lecture on how bias variance trade-off of random forest works. In the case of decision tree, bias variance trade-off works based on the depth. In the case of random forest, let me repeat, in the case of decision tree, the bias variance trade-off works based on the depth. In the case of random forest, we actually train deep trees of full length, but we control the variance or reduce the variance using more number of base learners. This is one key difference. The second key difference is feature importance. In decision tree, if you recall, how do you compute feature importance of feature fi? We see where all fi, feature I, is used in a tree. So let's say my feature fi is used. Let me say I'm assuming I'm using this particular feature here, and also, yes, just let me write like this, here and here, isn't it? Let's say fi is used in two places, and so on, so forth. We actually take an aggregation, we take weighted sum, isn't it? Let me say fi is appearing like this. Overall reduction in the case of decision trees, overall reduction in entropy or Gini impurity because of this feature at various levels in the decision tree. Of course, we have weights, we have more points here. Just see here, let me say this is my as we are saying, this is my first fi, this is another fi, isn't it? This is fi. Here if I see or here you have more points at this place you have more points, isn't it? You have more points, but here you have fewer points, isn't it? Or fewer points. So there is some weighted, there is some weighted scheme works out of here. The intuition is basically feature contributes to reducing. The intuition is basically which feature contributes to reducing your entropy or reducing your Gini impurity. In the case of random forest, the same thing. So wherever in decision tree, now what we done here, you look at overall reduction in entropy. In the case of random forest, overall reduction in entropy, capital H, or Gini impurity, Ig, because of this feature, because of feature fi at various levels, each of our base model MIs, isn't it? So here you have only one. In the case of decision tree, you have only one decision tree. isn't it? Here you have only one decision tree. In the case of random forest, you have k decision trees. Here you have k decision. Here you have k decision trees, isn't it? We see if a feature is used in lots of decision trees, and in each decision tree, if it is important, overall for random forest it should be important. So feature importance in decision tree and random forest are very similar, except that in the decision tree we are looking at the reducing entropy or Gini impurity at various levels in single decision tree. It is, if it is decision tree, it is single. We are looking at single decision tree, isn't it? Here in random forest we are looking at multiple trees. In the case of random forest we are seeing at multiple trees, multiple trees overall reduction, because of feature fi at various levels in each of the base models, m1, m2, so on. Let me say mk. So we look at reduction in each of the decision tree based on the scheme of decision tree, and we combine all of them to see a feature is important in random forest. So even feature importance in random forest is very similar, intuitively thinking like decision trees, except that now you have k decision tree instead of single decision tree. The rest of the cases except for bias variance trade-off and small difference with feature importance, except that most of the cases that we have seen for decision tree, your decision tree works well or does not works well, more or less same cases for random forest. I will repeat, your decision tree works well or does not work well, more or less same cases for random forest. By the way, random forest does not work very well, especially when you have categorical features with many features, and especially when you do one hot encoding. This is very similar for you, similar to decision trees. So when you have extremely large dimension, isn't it? Random forest has very similar property to decision tree, except in the case of bias variance trade-off and feature importance. Just go through this lecture. Actually, I can say this lecture is little bit repetition of previous lectures. Just go through this. If you have any difficulty, please keep a comment. Thank you very much.